In this example, I'm going to demonstrate how to graph linear functions using Webassign. And this particular question says that we have an object moving with a constant velocity of -3 meters per second. So I know that it's constant velocity because I see that the velocity value is just a number. There's no variable involved, there's no t for time, for example. If it had said v equals 3t, then the time would affect the velocity. But here, there is no time, so the velocity is just constant. Now, whenever we have constant velocity, we're going to have graphs where they're both going to be linear, the position and the velocity. But when it comes to the velocity, it's probably the easier one to graph because they're saying the velocity is always -3, which means it's -3 at the start of the clock, and this is the time axis here, and this is the v-axis. So it's -3 at the start of the clock, it's -3 after a couple seconds, and it's -3 after that. It's always -3. So the type of graph we expect to see would be a horizontal line. So you just want to connect those points like this. And that's it for our velocity graph. So when we go to Webassign, find the velocity versus time graph, and we have to plot that horizontal line. One of the most common mistakes that occurs is sometimes people will select the point tool, several different tools you can pick from. We actually want the line, but sometimes people will put various points into their answer. But the way Webassign is programmed for this question is that it won't accept any points being in your answer. Even though it's not really mathematically wrong to have those points there, Webassign just can't understand it. So if you would just remove any points, then you'll be all set. We want to select the line tool, and we don't want a segment or array for this question. We want the line with 2 arrowheads. And the reason is that in the beginning of the question, they said that the time domain was anything from -infinity to infinity, and the object holds this velocity that whole time. So we want that kind of response. Now, when you're doing your position graph, that's a little different. So there's a formula for position when it comes to a constant velocity object. The formula is x equals vt plus xi. It makes a linear graph, so this could be a line that's slanted. It might be slanted up, it might be slanted down, depending on your velocity. So in our case, they said that the v velocity was -3, so just plug that in for the slope of your line. Xi stands for the initial position of the object. And so what we want to look for is some information about the initial position. And that's given right here. What this says is the position of the object at time 0, at the start of the clock, is 1 meter. So for this graph, the time axis is t, and the vertical axis here is actually x, which is a little different from a lot of math problems, but that's because it's an application of linear equations, where in science, oftentimes position may be given the variable x. So we want to plug in this initial position into our formula, and then we have something that we can graph. So just put that 1 meter into xi. And that's the graph that we want to make now. Once again, you want to select the line tool. You can click on your intercept, and then using your slope, you want to create your second point. So the slope was -3. So if we go over 1 to the right, then we have to go down 3 units according to the slope that was given. And so that could be a correct second point there. And you just want to hit submit answer, and hopefully it'll accept. Okay, it accepts. So in this next problem though, we're given a piecewise defined velocity function. What this says is that the velocity of the object changes at one particular instant of time. There's a sudden change here at a time of 3. So our velocity function starts out at a value of 2 for any time that's less than or equal to 3. Let's sketch that freehand real quick. Three is an important time. Now what happens at 3 is there's going to be a value of velocity equal to 2 leading up to when the clock strikes 3 seconds. And even when the time is 3 seconds, the value of the velocity is still 2. Then suddenly it jumps to a new value of -1. So we're going to have this. Both of these are constant velocities over the interval that they're happening. It's just that at 3 there's this sudden change. And we're going to have an open dot for this segment because of the fact that they said it was going to hold a value of -1 only when t is greater than 3, not when it's equal to 3. So this would be the kind of graph that we want to make. It should continue in both directions forever. So let's see if we can plot this in Webassign. You have to go to the v versus t graph. Okay, so what I'm going to try to plot here is a ray that starts out at the coordinates 3, 2, and then it goes through some other point such as 0, 2. Let's see if we can do that in Webassign. Select the ray tool with a dot at one end and an arrow at the other end. Click on the important point in question, which is 3, 2, and then click on any other point where the value of the velocity is 2 and to the left of the original point. And that's what we need for that segment. Now we're going to try to plot this one, which points to the right. So let's click the ray tool again. It will put another ray, but this time at -1, and click another point which is to the right of that. Now that's pretty good. We've got 2 rays. One thing is though, we have to make our second ray here have an open dot at the time of 3. We can't have a closed dot above and a closed dot below. So if you click on the dialog at the upper right, you can select the different rays and just make sure that your ray, which is pointing to the right, has an open dot on it. That should do it. It'll accept that. Alright, so we got credit for the velocity. Now we just have to plot the position. So for that, we need some more information. In the instructions, they say that our object at time 0 is located at the origin of this coordinate system. So the vertical is the x, the horizontal is the time, and they're saying that our position at time 0 is 0. So that's starting out right here. However, we have to think about what our graph looks like around that region. So we have this motion formula which says x equals vt plus xi for constant velocity objects. And we know what the velocity is in this region. The velocity is 2, according to this part of the piecewise definition. Since the velocity is 2, we have to figure that the slope of the graph is 2 at t equals 0. So we have x equals 2t plus 0 as a formula for the graph at that time. The xi is clearly 0. They said that right here. So we just have to sketch a graph where there's a slanted line whose slope is 2 at that time. Okay, that'll continue forever as we go to the left. However, on the right, there's going to be a sudden change in the velocity at this point. And what does it do after that is the question. So if we look down at the velocity graph, we see that the velocity jumped from a velocity of 2 down to a velocity of -1. So our graph is going to change direction because of that. What this indicates down here is that the slope of our position time graph needs to now be a -1. So we might see something like this. And that'll be what we want to graph. So one thing that you might be asked is to come up with a position that's defined in a piecewise way based off of the piecewise defined velocity function that you were given. So the given was that we held a value of 2 anytime t is less than or equal to 3, and then a value of -1 if t is greater than 3. We want to use that idea now to come up with formulas for the position. I actually already did the first one. Anytime t is less than 3, we're going to be following this formula, x equals 2t. So we can write that here, that the position will be given by 2t as long as t is less than or equal to 3. But at 3, there's this sudden change. Okay, so this is the left side of our graph. But now we have to examine the right side. Now for the right side, we'll start with that same linear equation. But we want to plug in the new velocity. And the last thing we have to figure out is what this xi would be for this segment. So you can't actually use the xi that was given in the instructions here. The reason is we're trying to figure out what the intercept of this line would be if the line was extrapolated back in space, going in the same direction that it's going until it hits the vertical axis. This is going to be the b, the intercept that we actually need for this part of the problem. All right, so I'll just call it b for now. And what we want to do is use a point that this line goes through in order to discover what the b really is. So there's one point here we have that we could give coordinates for. We know the horizontal coordinate is 3 seconds. So it's 3 comma something. And then we just have to figure out how high off the time axis is it. So earlier we had a formula for predicting positions based on times. So if you know the time, you could plug it in and get the vertical value. So plug in a t of 3. So x at t equals 3 is going to be 2 times 3 plus 0. So the x at t equals 3 will therefore be 6. And that tells us what the height of that point would be. It's 6. Now that we know this, we could use that combination in the equation that we have below. So I'm going to plug in a combination of x and t that I know this line goes through. We can see that the line will definitely go through the point 3 comma 6. So plug in 3 comma 6. The 3 is our time and the 6 is our position. So we'll get 6 equals negative 1 times 3 plus b. And what I'm doing there is I'm replacing the x and the t with the values that we got from the point that the line goes through. We'll get 6 equals negative 3 plus b, add the 3, and 9 is b. So the equation of that second part of the problem then, it must be negative 1t plus 9. And according to the picture that I drew, that seems to make sense, that this b could be 9 units off the time axis. Alright, now that we have this, we can now plug it in. We'll get negative 1t plus 9 for whenever t is greater than 3. Let's try to plot this now in Webassign. We already plotted the velocity. Now let's plot the position. Now once again we want to select the ray tool and we want to start our drawing on a point that we know the ray terminates at. So this ray, according to my drawing, terminates at 3 comma 6. So let's start it off at 3 comma 6. And we also know that it goes through the origin, this ray. We were given that right here. We can see it here. All right, so that's one of the rays we need. Now we need another ray, which terminates at that same location 3, 6, but this one goes to the right and down. So to the right 1 unit and down 1 unit is the slope of it. So click the ray tool again. We can start here at 3, 6, and then just give ourselves a slope of -1. And that should do it. You can always adjust your points that you entered by clicking on the different ray dialogues and make sure they're correct. Another point to mention is the way this question was programmed. We just want to use solid dot for both the rays. Webassign doesn't want open dot for this particular graph.